In this lecture, we're going to look at some links between set theory and the logic that we've been studying recently. We start by introducing a new idea about propositions over a universe. So to think about this, start by thinking about the sentence, "It was a rainy day." Now, as it stands, this is not a proposition because we don't know whether it's true or false. Whether it's true or false depends on what this "it" was, specifically which day. If it happens to be a day that was not rainy, then this is false. If it happens to be a day that was rainy, then this is true. But we need to know which day it is. So in some ways, we can consider this "it" as a variable, and as soon as we substitute a value, in this case a specific date, into the value of "it", then what we have is a sentence that becomes a proposition that we can say is either true or false. For example, we might restrict the value of our "it" in the sentence to all the days between the 1st of January 2018 and 1st of July 2018 in Cape Town. So then we've been quite specific. You might want to be a little more specific, giving times and things like that, but at the moment this is pretty clear. And in this case, we can say that the sentence is a proposition over the set of days between 1st of January 2018 and 1st of July 2018 in Cape Town. So we have a proposition, and it takes as possible values of a variable within it things from this set. So this leads us to a very useful idea, which is the idea of a proposition over a universe. Let U be some non-empty set. Then a proposition over U is a sentence that contains a variable that can take on any value in U and that has a definite truth value as soon as you've put any substitution in that variable. So for example, if we're looking over the integers, so these are propositions, and any variables in these propositions take values from the integers. So we can have a look at, here's a proposition, 4x squared minus 3x equals 0. Then we can decide if this is true or false, given that x must be an element of integers. We could also have 0 is less than or equal to n is less than or equal to 5. And if we're thinking about n taking on all the possible values in integers, there are some integers for which this proposition is true, and there are some for which it is false. For example, if n is equal to 42, then that proposition is false. But if n is equal to 2, then it's true. And similarly, here's a proposition, k is a multiple of 3. So again, k is allowed to take on any value of integers. And then we can decide, depending on which k we put in, whether this is true or not. But you could also have propositions over the rational numbers. So now we're saying x has to come from rational numbers. And some may be true and some may be false. You could also have propositions over the subsets of the positive integers. And again, thinking about each of these will help you decide if they're true or false, assuming that you're putting in positive integers. So now we're taking all the laws of logic that we've learned and we're applying them to propositions over a universe. So now we have a universe, we can decide, given a particular proposition, for which values in the universe the proposition is true and which it's false. And we define the truth set of a proposition, which we denote T sub P, as the set of all elements in the universe that we're looking over for which our proposition is true. So for example, if we want to look at the examples we just saw, so now we're looking over the integers, we'd like to find the truth set of this proposition. So I'm going to call this proposition P. So our truth set for this proposition P is going to be the set of all x in integers for which our proposition is true. So for which it is true that x squared minus 3x is equal to 0. So let's see if we can actually figure out which integers belong in here. Well, this is going to be the set of all x in integers, such that, and notice that we can take out a common x, so that we've got 4x minus 3 is equal to 0. And now we see, well, we can't find any integers for which this factor will be 0, but we can find a value for an integer for which that is 0. So it turns out that for this proposition, our truth set over integers is just 0. And if you had a look for this proposition, you would see that the truth set is 0, 1, 2, 3, 4, 5. And for our third proposition, it's going to be all the multiples of 3. So and so on. So the thing to notice is that your universe is quite important. So if we have a look at part B, if we look at the same proposition here, but I'm going to call this Q because we're over rational numbers now, so I want to just be a little bit careful. My truth set for this is the set of all x in rational numbers, such that 4x squared minus 3x is equal to 0. And now we can see that there are actually two rational numbers in this truth set. It will be 0, which was also in our integer set, but we're also going to have 3 over 4. So it becomes important to be very clear which universe you're working over, because it's going to affect your truth set. So spend a little bit of time seeing if you can figure out what the truth sets are for each of these various propositions. And remember, the truth set might be empty. It might be that there are no subsets of positive numbers for which any of those are true. You just have to check. So we can think about tautologies and contradictions over a universe, and they are pretty much what we've seen before. So a proposition over our universe is a tautology if its truth set is the whole of the universe. On the other hand, it's a contradiction if its truth set is empty. So if we think about, for example, s minus 1, s plus 1, which is s squared minus 1, this is a tautology over the rational numbers. Why is it a tautology? Well, it's true for all rational numbers. There's any single rational number that you happen to pick, this is going to be true. You substitute in your rational number there and there, and you'll find that you have the same things on either side. On the other hand, if we look at x squared minus 2 equals 0, you cannot find a rational number for which this equation holds, because the square root of 2 is irrational. So now we're going to have a look at the link between our logic and sets that we've been working on. Specifically, there's a very nice link between our OR and union and intersection. So to see this link, we're going to start by looking at the truth set for proposition P or Q. So if we write this out using set notation, this is going to be all the elements in our set U, such that P when applied to A or Q when applied to A is true. But if we think about this, if we're drawing a little sketch over here, if I've got my proposition, so I'm going to have TP, so this little set is a set of all elements for which P is true, and I'm going to have TQ, that's the set of all elements for which Q is true, and what we want is all the A's which lie in either TP or TQ. Well, so what we're really saying is we want all the elements A in U such that A is an element of TP or A is an element of TQ. But really this is just asking us for TP union TQ, because that will give us all the truth element, all the elements which are either in TP or in TQ. So our truth set for P or Q is the union of TP and TQ. So this shows quite nicely the link between our OR and our union. On the other hand, if we're looking at the truth set of P and Q, then we want to have the set of all elements in our universe such that PA is true and Q of A is true. And by using the same reasoning, we can see that our truth set for P and Q must be the intersection of our truth set for P and our truth set for Q. So take a moment to go and draw the Venn diagram and convince yourself. So there are two more of our basic propositions that we want to think about. We want to think about implication, and we also want to think about biconditional. So we're going to spend a little time drawing diagrams for those. So if we're thinking about implication for propositions over a universe, we know that if P and Q are propositions over U, P implies Q if P implies Q is a tautology. So that's what we're meaning by implication. So we're saying P implies Q gives us ones or truth for all values of P implies Q. So here it's quite useful to remember that we can rewrite P implies Q as not P or Q. So if you don't remember where this comes from, head back one lecture. We can write both our implication and our biconditional implication as using only ORs. So now if we use our same Venn diagram logic, what we want is, so we're going to see where the coloring comes in here. I've got my truth set for P and I've got my truth set for Q, and I want to have the union of the truth set of not P and the union of the truth set of Q. So if I fill that in, I've got the truth set of not P is everything outside of the truth set of P. And if I've got the truth set of Q, that's going to be all these things inside there. And putting the union together, we get the blue coloring in over here. So if you're wanting to think about, so if you wanted to write in the solution, the truth set of P implies Q is the truth set of not P union the truth set of Q. So if we think about how this might look, if we're looking at the natural numbers, then we can say n is less than or equal to 4 implies that n is less than or equal to 8. So if n is less than or equal to 4, then we know that n is less than or equal to 8. that is absolutely true, since the truth set of n is less than 4 is contained in the truth set of n is less than 8. We can look at a slightly more tricky example. So of the power set of integers, okay, so we're thinking of the set of all sets of integers. Let's see what this means. If the size of a complement is equal to 1, so the complement of some set has a size of 1, then it must be true that our original set intersection 0, 1 is not equal to the empty set. So this takes a little while to think out. The diagram I think of when I do this is I'm imagining that I have my universal set, which in this case is all integers. So I've got all my integers sitting around over here. And I have some set A such that its complement only contains one element. So I'm going to imagine that this little bit over here is a complement and everything else in here is A. So A complement just has one element in. We don't know what it is. So let's now think about our conclusion that we get. Well, we know that A must have at least more than one element because the integers are infinite. So the size of A is definitely bigger than 1. So if it's definitely bigger than 1, then it's definitely going to have either 0 or 1. Because a complement only has one element in it, so at most it could have 0, and if it has 0, then A will have 1, or if our A complement contains 1, then our A must contain 0. So we know that if we take our intersection of A with the set 0, 1, one of those must be an A, so we won't get the empty set. And I'm going to leave you to think about this final little implication here. Okay, now we want to think about equivalence of propositions over a universe. So now we're thinking two propositions are equivalent if the biconditional property is a tautology. In terms of truth sets, all we're saying is that the truth sets of P and Q must be the same if our propositions are equivalent. So some examples of those that we can look at: n plus 4 equals 9 and n equals 5 are equivalent propositions over the integers because the truth set for n plus 4 equals 9 is 5 and the truth set for n equals 5 is 5. And you can think through why these two are equivalent propositions. So although you probably haven't realized it, when you've been solving equations ever since you were knee-high to a grasshopper, you've actually been finding truth sets over various universes.